Hey, what's up everyone? Hope you're enjoying whatever is going on right now. Before we start, you guys are gonna need your Unit 11 packets out. I have it open to page 7, so pause the video and get that ready. So your last assignment, you were working on stoichiometry calculations, and it looks like a lot of you guys were doing a good job with that. But now we're gonna get to the real purpose for what we do those calculations for. That is theoretical yield, limiting reactant, and excess reactant. So on page 7, we're gonna find examples of this. But I wanna show you a visual of what this looks like. So I got these different colored pieces of paper. These represent some reactants in a chemical reaction. I've got orange ones and I have blue ones. Now in this reaction, what we're gonna see is that one blue and one orange are gonna come together to produce our product. So we've got a reaction here. One product is created. We've got another reaction here, another product's created, and so on. Now what we see is after we've undergone our reaction, we ran out of blue pieces of paper and we still have leftover yellow pieces of paper. So here, what we have, that brings us some vocab terms. We've got a limiting reactant and an excess reactant. The limiting reactant is the reactant that was used up or limits the reaction from continuing further. And the excess reactant is the reactant that was left over after the reaction has stopped. So what we could say here is that our limiting reactant, or the reactant that we ran out of, was the blue reactant, and the excess reactant was the orange. And what we're gonna see is in chemical reactions, usually we're gonna have something run out before the other, and that's what's gonna stop the reaction from continuing on. So now let's take it to an actual example that we may see in chemistry class. This is your first example in your packet on page 7. We're gonna start a little bit simple, and then we're gonna work our way to a little bit more realistic type calculations that we're gonna see in the future. So here we have a chemical reaction. We have magnesium reacting with oxygen to produce magnesium oxide. What is the greatest amount of magnesium oxide in moles that can be made with 7.8 moles of magnesium and 4.7 moles of oxygen? It's asking what is the limiting reactant, what is the excess reactant, and how much is left over. So based on the given values, we're going to be able to determine a lot of information. Limiting reactant, excess reactant, our theoretical yield, which is how much we're able to produce, and then how much excess is left over. When you have a chemical reaction, of course, the first thing that you always want to do is make sure that that reaction is balanced. So when we look at this reaction, we have 2 oxygens, but I only have 1 on this side, so I'll put a number 2 right there. And then we have 2 magnesiums now, so I'm gonna have to put a 2 in front of magnesium. Always want to make sure your equation's balanced, no different than what you're doing in stoichiometry, but that's super important when we're doing these calculations. So now, we want to see how much magnesium oxide can be produced from 7.8 moles of magnesium, and then we also want to see how many moles of magnesium oxide can be produced from 4.7 moles of oxygen. So we're going to need to do 2 different calculations here. First, I'm going to go from moles of magnesium to moles of magnesium oxide. We're going to do that first. So we started with 7.8 moles of magnesium. Set up our T-chart. Now using the balanced chemical equation, we have 2 moles of magnesium for every 2 moles of magnesium oxide. Moles of magnesium oxide cancel. 7.8 times 2 divided by 2. When you plug that in, that just basically is 7.8 times 1. So that's going to be 7.8 moles of magnesium oxide. So based on this, if I put in 7.8 moles of magnesium, I'm going to be able to produce 7.8 moles of magnesium oxide. Now let's see how much magnesium oxide we can produce from 4.7 moles of oxygen. 4.7 moles of O2. We have 1 mole of oxygen for every 2 moles of magnesium oxide. This cancels. 4.7 times 2 is 9.4 moles of magnesium oxide. So what you can see here is that we just did stoichiometry. Nothing new here, except for now we have two different answers. Now we want to compare these answers to see which one of these reactants, magnesium or oxygen, ran out first. The substance that's going to run out first is the one that's going to give us the smallest amount of product. So with 7.8 moles of magnesium, we were only able to produce 7.8 moles of magnesium oxide. When we had 4.7 moles of oxygen, we were able to produce 9.4 moles of magnesium oxide. So your limiting reactant is always going to come from the reactant that produces the least amount of product. In this case, 7.8 is smaller than 9.4. So my limiting reactant then is magnesium. That means that my excess reactant, the reactant that's going to be left over, because we can only produce 7.8 moles, is going to be oxygen. And then my theoretical yield, your theoretical yield is the amount that you produce from the limiting reactant. We determined that our limiting reactant was magnesium. Our limiting reactant produced 7.8 moles of magnesium, so my theoretical yield is 7.8 moles. All right, so now we're able to determine how much our theoretical yield was, 7.8 moles of magnesium oxide, what our limiting reactant is, and what our excess reactant is. The last part of the question is now asking what is in excess? Well, oxygen's in excess, and now we want to know how much of that oxygen is left over. So we need to use the theoretical yield. We want to see of this 7.8 moles of magnesium oxide that we produced, how much of these 4.7 moles of oxygen was used. How much oxygen did we actually use? So we need to do one more stoichiometric calculation, 7.8 moles of magnesium oxide. If you have 7.8 moles of magnesium oxide, there are 2 moles of magnesium oxide for every 1 mole of oxygen, because that's our excess. 7.8 divided by 2 is 3.9 moles of oxygen. So if I started with 4.7, I only need to use 3.9 for this reaction to take place. I'm going to subtract 3.9 from 4.7, and I'm able to determine that 0.8 moles of oxygen are actually going to be left over after that reaction takes place. So from all this information, my theoretical yield, or how much I can actually produce from the reactants given, is 7.8 moles. My limiting reactant is magnesium. My excess reactant is oxygen. My theoretical yield is 7.8 moles, and I have 0.8 moles of oxygen in excess. So there's your first example right there. Let's take it to a little bit more serious example. All right, again, we have a chemical reaction. We want to figure out what the limiting reactant is, what our excess reactant is, what our theoretical yield is, and then how much is left over in excess. Okay, so we have a chemical reaction, aluminum reacting with chlorine to produce aluminum chloride. We want to know what is the greatest amount of aluminum chloride in grams that can be produced from 114 grams of aluminum and 186 grams of chlorine. We want to know the limiting reactant, the excess reactant, what our theoretical yield is, and then how much excess is left over. So before we do anything, let's balance our equation. Two aluminums, 6 chlorines, balanced. All right, so we want to see if we have 114 grams of aluminum, how much aluminum chloride can we produce? Now we're getting into the full length stoichiometry where you need to convert from grams of one thing to grams of another. So I'm going to walk us through that. Aluminum has a mass of 26.98 grams for every 1 mole. There are 2 moles of aluminum in the equation, and there are 2 moles of aluminum chloride. For every 1 mole of aluminum chloride, we have a molar mass of 133.33 grams. So once we plug this in, we cancel out all these units. That's going to give us how much aluminum chloride we can produce, which comes out to 563 grams of aluminum chloride. So with 114 grams of aluminum, we could potentially produce 563 grams of AlCl3. All right, now let's see, with 186 grams of chlorine, how much aluminum chloride can we produce from that much starting product? So the mass of chlorine for this is 2 times that of chlorine because it's Cl2, so it should be 70.9 grams for every 1 mole. In the chemical equation, there are 3 moles of chlorine for every 2 moles of AlCl3. And then 1 mole of AlCl3 has a mass of 133.33 grams. Let's cancel out those units. Went from grams of chlorine to grams of aluminum chloride. When we plug that in, we come out to have 233 grams of AlCl3. So we need to compare these values. 233 is certainly smaller than 563. So this means that when we mix these 2 reactants, 114 grams of aluminum, 186 grams of chlorine, the most that we're going to be able to produce is 233 grams of aluminum chloride. That's going to be our theoretical yield, 233 grams. That 233 grams is produced by the limiting reactant, which is chlorine. And that means our excess reactant is the reactant that is able to produce more. Our excess reactant is aluminum in this case. Theoretical yield produces the smallest amount. This is our theoretical yield right here, which comes from the limiting reactant, which is chlorine. The excess reactant comes from the larger amount, which is aluminum. And then our theoretical yield is the smaller amount there. Now we want to figure out, of these 233 grams, how much of the 114 grams of aluminum do we actually need to use? How much is left over after the reaction? So we have 233 grams of aluminum chloride, and we're going to want to take this to grams of aluminum. The good thing about this is we already have the molar mass of aluminum chloride from previous, so we don't need to recalculate that. Aluminum chloride, there are 2 moles for every 2 moles of aluminum. And then 1 mole of aluminum has a mass of 26.98 grams. Just got to look at the periodic table for that. So when I go from grams of aluminum chloride to grams of aluminum, that comes out to 47.1 grams of aluminum. I started with 114. I only needed to use 47.1. So 114 minus 47.1 comes out to be 67 grams. So I have 67 grams of aluminum left over at the end of the reaction that I didn't even use. That's how much is in excess. So based on these 2 examples that we did, we were able to identify a limiting reactant, which is what runs out first, an excess reactant, which is left over. Based on those 2, the limiting reactant gives us our theoretical yield. And then we can figure out with our excess reactant how much is actually left over using the theoretical yield. I know that's a lot of calculations there. If you need to slow down the video, if you need to pause it at certain sections just to see where those numbers come from, I wanted to show you a couple of different examples that you're going to have to work through.